As Tom was saying, we have a YouTube sort of page slash, link where a lot of these lectures from previous years, in fact, last year and the year before, are there. So I would recommend, you could look at those before coming to lecture, or if you missed the lecture or in place of this lecture. And what I'll try and do is each one of the lectures from the first half of the course, I'm going to link it to usually a chapter in Prints and Links to give you an idea what you should read in the textbook. You don't have to know that textbook inside out, but you should know the sections of that textbook that are highlighted in these lectures, okay, where I say sections, okay. I will post the slides ahead of the lecture, okay, so that you can look at the slides before you show up here. That can help you make a decision. Do you want to show up here to interact live, to ask questions if something's confusing, or just look at the lectures, watch the video, and that could be sufficient. So very simple goals here. We're going to use two imaging modalities in this course principally: computed tomography, which uses X-rays, and MRI, which uses radio waves, remarkably, to make images of human beings. Okay. And we're going to give you the tools to quantify things such as signal to noise in the image, contrast to noise. What is the spatial resolution? What's the smallest thing you can resolve? Say that again. Oh, yes. Oh, thanks. It's so tiny. All right, let's try and put it down here. Okay, good. Thanks, Tom. And so we'll give you the mathematical techniques, that are required to evaluate the imaging method. Along the way, we'll look at some current applications. MRI and CT are ubiquitous in medicine now. If you go into an ER, it's like a 50% chance that you're going to either get an MRI or a CT before you get out of there, right? And for good reason. When you see these pictures, basically the bottom line is, you want to know what's going on, you take one of these images, right? And you can usually see the source of a pain, you can see what has changed over time, etc. So it's used a lot. And both of these techniques are highlighted a lot in the increasing expense of healthcare because they are used so often. When you see the pictures, if it's my mom or my sister, I'm going to take the picture, right? They're amazingly good. So also, we want you to get some physical intuition about the underlying physics of how the signal is created in the first place. What is the signal, right? And it's different than photography, where it's just reflected light. It's actually, in one case, a shadow is cast, an X-ray shadow. So you have like an X-ray flashlight, you cast a shadow. That's the signal. And in the other case, you place a patient in a very high magnetic field. You bathe that patient in radio frequency with an antenna. You shut that off and then listen. And a very small signal comes back in radio frequency. It's quite remarkable. And you use that very small signal to make these amazing pictures with magnetic resonance. So this is the basic outline of how imaging works, the way we're going to look at it. And we have an object. And let me see if I can make this pointer get a little brighter. Can you see that pointer? Yeah, okay. So here's our object. In this case, this is called an axial slice through a human brain, right? So through somebody's head. And the imaging device will receive signal that has been modulated by that object. It's either been created by that object in MR, or it's been modulated as the X-rays pass through it. And our imaging device collects that signal, usually over the course of some time, right? In MR, it can take tens of minutes to collect all the signal you need. In CT, it can take 10 milliseconds sometimes. The data that is inside our imaging system is called the raw data. Those are the measurements we've made, and they have noise on them, and they have artifact on them, etc. And they have the underlying physics on them. In MR, this raw data turns out to actually be the Fourier transform of this object. That's why I asked you about the Fourier transform. Very good to know that thing, because in MR, that's what it is. The inverse Fourier transform of the raw data gives you the object. It's pretty simple. In CT, it's different. It's a little more complicated. There are projections of X-ray shadows through the object taken from different angles. Many, many reconstruction algorithms have been proposed to take those raw data and turn them into a replication or a facsimile of the object, right? That's a cottage industry. There's literally tens of thousands of scientific papers written about how do you take this raw data and make the best picture from it. Very fundamental questions are here. How much raw data do you need to make a really good picture? What is a good picture? Right? When do you say that picture is good enough? I can now stop taking raw data, or that picture is not good enough yet. I need to take twice as much raw data. So all those questions are laid open, right? A ton of engineering goes into this part. If you get a job in a medical imaging company, such as say Siemens, GE, Canon, one of these big companies that make these heavy iron imaging devices, a lot of engineering ingenuity and know-how goes into extracting that raw data. How do you do it most efficiently? How do you do it with the highest fidelity? Right? So let's look at a brief history of X-rays and MRI. At the turn of the 19th century, Röntgen discovers X-rays just in his laboratory. And that same year, he takes a picture of his wife's hand, right, on a piece of film. About 50 years later, two folks, one on the West Coast, one on the East Coast of the United States, simultaneously discover nuclear magnetic resonance. And it turns out that protons inside the nucleus have a spin. They're spin 1/2. And if you know what a Stern-Gerlach experiment is with an electron, you shoot it through a magnet, it's either going to go up or down, depending if it's spin up or spin down. Right? Same thing for protons. They have a spin. And the absorption of radio frequency occurs at a specific frequency where that spin changes state from being up to down. Right? So that's what NMR imaging is based on. But these guys discovered it just as a phenomenon, just like, oh my goodness, if I put RF in this sample, I see it get absorbed at a specific frequency. Right? Fast forward to the 70s, and Gregory Hounsfield took the X-rays from different angles and made a CT scanner, proposed CT scanning. About the same time, Paul Lauterbur in, I think it was Illinois at the time, did a similar thing with magnetic resonance signals and took projections through an object and made a picture of two test tubes. So that's, about 50 years ago, both of them now. So here's Röntgen, right? And here's Frau Röntgen's hand with, obviously she got a ring on that hand, it's a pretty big ring, right? And that ring really attenuates X-rays because it looks kind of dark. So, this is one of the most famous X-ray images. In the modern case, we have an X-ray source, or say an X-ray light, X-ray flashlight. It's called an X-ray tube. It's about something this big, and it produces a beam of X-rays. It's about the size of a loaf of bread. And these, X-rays come out of our source, and they pass through the patient and hit the detector. And the detector traditionally has been something that a phosphor screen that flashes, and then you put film behind that and you expose the film. So you just take literally a photograph of the phosphor flashes when the X-rays hit them. If the X-ray gets stopped by the patient, then you start seeing contrast, right? So in the lung, more X-rays get through than say in the heart or the spine. More X-rays get stopped. So it's a shadow, right? Normally, you don't look at the phase of that radiation as it hits your detector. You just look at them as particles or bullets, right? They're X-ray bullets. And they just tick, 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 hit your detector. And that shadowgram has been used since soon after Röntgen discovered X-rays. Chest X-rays have been used for a long time. Here's an example of an early chest X-ray machine. There's a very high voltage source here. They accelerate electrons to hit a target to make X-rays spray out here. And this poor devil, who's the patient, is holding the detector in front of their chest, right? And so as the X-rays pass through his body, they're going to either hit the detector or get absorbed by the patient, right? To produce a chest X-ray. And so though that's been, I think in World War I, they started using this imaging technique in the field, actually, to discover where people have been shot, et cetera. So it's been around a long time. This is a modern X-ray system where the X-ray source is here. So there's a tube in here that creates the X-rays, like an X-ray bulb, flashes through the patient. The detector is in this table behind the patient. And why this lucky fella is looking at what's called a barium milkshake. And you're going to take that milkshake and you drink it. And then they'll take the X-ray source and pass it down and continuously take pictures as the patient swallows that milkshake. So you can actually see the esophagus moving. And if there's some problem in how the patient is swallowing, it's easily observed. This is just one form of X-ray machines now. There are many, many forms of X-ray imaging machines. This is a form of an X-ray imaging machine, probably sometime in the 40s, I'm guessing, in which shoe stores started buying X-ray systems, such that when you tried on a pair of shoes, you could, in fact, have an X-ray source here, look through your feet, and the X-rays would hit your eyeballs, right? Or the phosphorus in front of that would basically light up, and you could see your toes and wiggle your toes and determine whether your feet are fitting into that shoe just right. I would not recommend this product, right? That went by the wayside. So here's what a chest X-ray looks like in a patient who has basically some kind of inflammation in their lung. It's more than likely pneumonia. This is one of the most common things, diagnosed with a simple chest X-ray, but you can see that it casts a shadow. So there's more fluid in that part of the lung than in the other lung, and in this patient's left lung. And that indicates that there's some kind of inflammation, right? This profile here is the heart, right? So it's stopping more X-rays than the lung tissue because the lung tissue is mostly air. And you can see the bone does a good job at stopping X-rays. So for imaging, whether or not you've got a broken bone is perfect. This is a mammogram, and this is high resolution planar X-ray imaging where you put an X-ray detector flush against the side of a woman's breast, and you shine X-rays through the breast, and you look for abnormalities in the picture. It's a very difficult image to read, actually. It's very subtle findings on these. And this is if you make a CT of this, so you isolate the signal from a single slab or plane in the breast, and then you can see that certain lesions start to pop out and become far more evident than when you project the signal through the entire breast, right? So that's a hint that perhaps we should do 3D imaging, CT imaging, and look at the whole 3D volume instead of a projection through the entire volume. I've watched people read these when I was at Hopkins as a young faculty. We spent a week with someone reading mammograms, and it's a tough job. The lesions on a mammogram are really subtle. And if you call it positive, that patient has to go for a biopsy usually, which isn't, a pleasant procedure, right? And if it's unnecessary, that's not a good thing. And so, you have this critical decision at that point, and you say, well, I don't think it deserves a biopsy. The patient comes back 2 years later and they're positive, right? Because the lesion's grown, and then you biopsy and it's positive, and you look back 2 years and you go, oh man, should I have called that thing positive? It's really, really tough, right? Yeah.
Do they still call those by hand, or do they use like machine learning?
So great question. The question is, so like we get it on here, is do radiologists still call these by hand, or does a human actually read these versus a machine? And deep learning, as we have seen, is taking over a lot of human perception tasks, radiology being one. And I would say deep learning algorithms do just as well as humans on this, is the sort of data right now. And more than likely in the next 5 years, they'll get better than humans, right? If you just go on brutal statistics of like, does it pull out with the best sensitivity specificity? That doesn't take into account the patient, because the detector at that point isn't human, and it doesn't look over at the picture of the patient and see what else is going on in the patient's life to see where we are here, right? So, but just as a raw detector, I think they're going to be just as good as humans, right? Because what human can look at 1 million mammograms, right? These algorithms, 1 million mammograms, do that in an hour, right? And so you just gather them up and train it. And you have downstream data as to who's positive. So you develop these huge libraries of who actually went on to develop tumors, right? And so you should get better when you have a bigger and bigger database, right? So I think deep learning is going to take over a lot of detection techniques. Lung screening, very difficult thing when you're looking for small nodules in the lung to determine if they're tumors or non. So you want the highest signal to noise, good spatial resolution so you can see the texture of the lesion. And again, a human has to go through all of the slices of the lung and look over the whole scan field, right? A machine is going to do that better eventually. And then a human will come in with the ones that have been flagged and sign off, because a human has to sign off, right? And say, yeah, that's where we are. But it's a great question. I think deep learning, it's now radiology has a deep learning journal, right? And the number of papers that are being submitted to radiology conferences, half of them were deep learning over the last, 4 years or something. And so it's taken off. So this is an X-ray image of a patient's chest who's sitting on a fluoroscope, this is called. So this is an X-ray system, just like the one where you saw the guy with the barium milkshake, but this one, you lie on a table, the X-rays come out continuously from the source, and then underneath the patient, you have a detector it's essentially like a TV screen, right? And you're just watching continuous X-ray illumination. Normally, so in this case, it's 15 frames a second, and the X-ray pictures are derived from a flash, an X-ray flash. They don't, you don't keep the X-rays on for that whole 1/15 of a second. You just do a flash and do that 15 times a second. So the flashes are millisecond long, right? So you freeze motion. And here's the ribs background, and then this is the heart. But it gets really interesting when how do I do the pointer? Down here. I think I have to escape. Yeah, there we go. Okay. This is when it becomes marvelous. All right. Beat that. Right. So what's happening there is this plastic tube here, and that's what it is. It's just a plastic tube with an end that has the right curvature and the right little hole size, is plugged into the patient's left main coronary artery, right? So it comes over their aortic arch down towards the heart. The physician manipulates it manually, looks on the X-ray images continuously, plugs that thing into the left main. And then you inject a contrast agent through that tube into the artery. And so the only physiology that's getting the contrast are the vessels. And all of a sudden the contrast just jumps off the page, and you can see with great detail what the state of the vessels are in this patient. This is done tens of millions of times a year in this country because people in their 50s and 60s get chest pain, and you put them on the table and you inject this dye and you look and see if there's a problem with their vessels. It's the most common way to die when you're in your 50s and 60s, is just you have a heart attack. And so this picks up where the vascular abnormality is that is causing you the chest pain or is causing you the heart attack. And does anybody see the vascular abnormality on this? Hard, the contrast is not perfect in here. Maybe we could lower the lights. I don't, there's a huge bank of buttons here, but I'm not going to press them. Anyway, I'll get right to it. Right there, you see how it's sort of faded a little bit? That means the amount of contrast is less, and so the diameter of that vessel is less at that point, and so it's tightened down. One of the problems of this technique, obviously, is that you can see if we zoom around in time, over a couple of heartbeats, you see the contrast going down the vessel. That's really nice. But also, as the heart's moving, things are overlapped and then they're not overlapped, and so you can see that there's a vessel here, but that's actually two vessels, one on top of the other. There's the one on the bottom is there, right? And so it's an excellent X-ray imaging technique, but it takes some skill to read. And you also usually take different views. So you'll do, say, 3 injections and view those injections from different angles, right? Such that you can see around different vessels. Here, so you have to ask yourself, well, what's image quality in this instance? What are we interested in? We're interested in detecting that vascular abnormality, that thing right there, right? So we need the spatial resolution to resolve where it is, like, and ask what's the dimension of the vessel when it's thinned down. We need the grayscale level to be measurable with a good signal to noise so that we see that there's a reduction in attenuation at this point. And you have to have the time resolution because this thing's moving. So if it took 200 milliseconds to take this picture, the vessel would have moved a considerable distance and it would all get blurred out. So you need a flash. So there's temporal resolution, spatial resolution, signal to noise in order to achieve your goal, right? And depending on what your goal is, those parameters change, right? If you're measuring the dimensions of a tumor in someone's brain, you have a long time to do that. It's not growing, millimeters per second. It's just sitting there. And so you can take a ridiculously high resolution picture over a long time. Here, things are moving, right? So you need a different type of imaging device. Computed tomography, has a long history. In fact, it has a longer history in math. The math for doing computed tomography is very old. Remarkably, so here's radon, and we'll learn the radon transform. Let me put my laser back on. Here's, and it's critical for doing computed tomography, or at least it used to be. Deep learning might make it less critical, to tell you the truth. Although you have to reconstruct truth in order to teach a learning network. But anyway, Cormack applied the radon transform to tomographic imaging, right? And then Hounsfield, without knowledge of either of these two people, he's just happily doing his job at EMI, reinvents it all to make a CT scanner, right? And this is he had funding for this because the Beatles had just come off selling, 1 million records a month for EMI for the last 8 years before that. So they were just ridiculously flush in cash, and they let him build this crazy scanner, right? It was a CT scanner that took, half an hour to make one slice image. It didn't look good on paper when it started, but, we'll see where it's gone, and it's considerably improved. Let's just look at the basic principle of computed tomography. And if I have a set of X-ray beams that are coming vertically, say from up here, this is an imaginary situation where they're parallel. Okay, they're all shooting down parallel. And I have a detector down here. When I measure how many X-rays hit my detector, right, I'll get a signal that looks like this. If I have an occluder here, this thing is going to absorb more X-rays than the big circle. And the big circle absorbs more X-rays than, say, the background. But now I see two features. So this one's smaller, so fewer X-rays are absorbed. but this one is thicker, therefore you get a greater reduction in X-rays at the detector. So we have a profile now through the object. We know there's, looks like 2 objects in there that are absorbing X-rays. We kind of know the width of one of them or of both of them. We don't know where they are in the vertical direction at all. We have no information about the vertical direction. But if we rotate and shoot X-rays in a parallel direction this way, then we can get what the absorption looks like from that orientation. Right? That's pretty simple stuff. Right? You're just going to take a view this way, 90 degrees, take a view that way. And if I only have 2 objects, when I project back my estimate of, say, the ability of a substance to absorb X-rays in that whole column, this has high ability to absorb, so it's bright. So does this, it's a little less bright. And that's my one-dimensional image. If I do that twice, I get this picture, which isn't bad, right? You know, it's super low resolution, but it tells you basically, oh, I've got 2 primary objects there. And that's just for 2 views, right? So we'll see this principle is how CT is done. It's just you take 800 views instead of 2. And you just take many, many views, and then you get higher and higher spatial resolution estimates of where those X-ray absorption dots are. The detectors have been around for a long time. This is a one-dimensional X-ray detector, and it has you know, these elements here that are separated on the order of about 1 millimeter. And if I have a single source, I can just raster that source across this detector and get a profile, right, with virtually parallel beams of X-rays. That takes a long time. This was the way they did the first CT scanner. In the next generation, or a few generations later, you have a curved detector and a source that gives out not just one beam, but a fan beam of X-rays simultaneously. And so now I can take one shot and I will get many projections through the sample, right? And obviously those projections are at different angles as opposed to here where they're all parallel. So we have to take that into account. And then this is a modern CT scanner where you have a source and you have a detector that has about 1,000 elements this way, and usually around 256 elements this way. And this has been the major jump in CT technology, is piling up the detectors in this direction, in the Z direction. So you can think of each one of those rows as an individual CT scanner. And now I've got 256 CT scanners piled together, right? So the whole thing, you can image a chunk, something about that big, you know, 16-centimeter sphere in the middle of the scanner. You can image it with 1/2 rotation of the gantry of a CT scanner. So that's about 140 milliseconds. You can image that entire volume, right? Huge leap in speed and technology. This is how one vendor decided to speed it up as well. They put 2 X-ray sources on the gantry and 2 detectors. And so they simultaneously get, say, a vertical and a horizontal view of the sample, and then they rotate that. So that should just increase things by a factor of 2, right, in terms of acquisition speed. So it goes from 150 milliseconds for the whole volume down to 75 milliseconds for the whole volume. That's pretty nice. If your detector isn't wide enough to image the entire volume you're interested in, perhaps you want to go from the neck all the way down to the knees, then you can push the patient through the CT imaging device while the detector is rotating continuously and get essentially a spiral of data as the patient goes by. Right? That's called helical data. And you use that data to put together the whole 3-dimensional picture. This is actual data from the scanner we have over in the hospital, in the Jacobs Hospital. And we've had this for about 4 years now, or I guess 4 years, yeah. And it has 256 detectors in this direction, in the Z direction. And so you can see each one of those images as that detector is rotating around the patient is like a chest X-ray, right? And we're taking that chest X-ray from different angles continuously. And you can see the profile of the heart here. This is the diaphragm of the patient, the liver's here. The heart is sitting right on top of that. You can see some vascular features from the heart. This is the spine, which absorbs a lot of X-rays, so it gets in the way of what you want to see. It's kind of, you know, a bit of a pain. And you can see also that the signal gets a little nasty when we have a very long path that the X-rays have to come through, because many of the X-rays get absorbed and you're left with just a few, you know, like tens of X-rays on your detector. And so you get this very high noise at that time, right? However, if that noise is outside the field of view you're interested in, you can usually compensate, not let it wreck your picture, right? By filtering it in some spatial way. So is there any questions about the geometry here? This is like that geometry, yeah? Okay. Oh, okay. So about 1,000 detectors this way, 256 detectors that way. It rotates around the patient 4 times a second. So about 250 milliseconds for one full rotation around the patient. And you're taking approximately 1,000 views for each rotation, right? So that's the speed of the data coming out of the thing, which sounds like a lot. It is a lot. I mean, it was challenging for companies to do that. So here is a very early CT scan of somebody's brain, where they had that system that had a single source and it rastered across with the detector, and then they rotate and then do it again. So this scan, I think it takes 10 minutes or something to get this scan, and a long time to reconstruct it, but it's back in 1975, right? Here's a modern CT of somebody's head, 512 by 512 in about 140 milliseconds. So ridiculous increase in speed. Hence, when you have images of this quality, and somebody comes in and they've just come off the ski hill and they hit the dang chairlift pole or something, you don't say, oh, should I get a CT? No, you just get a CT. Just look and see what's in their head, right? Make sure they're okay, right? And if they have a bleed, it'll show up, and it takes 5 minutes, right? And so that's why 80 million CT scans are done in the US in 2013, right? So, you know, I'm all for reduction in healthcare costs. I think that's a good plan. This country has its issues with healthcare costs, which you can get the same kind of coverage and everything in Canada, Britain, whatever, and get these CT scans when you have an accident without having ridiculous costs. But that's a whole other topic that would take a whole other course. Here's somebody, this is a young woman, she was in her 20s, comes in with acute chest pain, right? So that could be anything, right? You're just like, oh, I got pain. Is it her coronaries? Is it an infection in her lung? Is it, you know, indigestion? What's going on here? Put it on the table and you look, and this is one of those scans where you had to push the patient through the scanner while you're continuously rotating. And you can see that there's this weird line down here in her aorta, right here. This is her descending aorta. It comes out of her heart, up the aortic arch, and then down this way. And this line here shows where the intimal tissue of the inside of her aorta has separated away from the aorta itself, right? So it's called an aortic dissection. Very rare in somebody this age. So you wouldn't, you know, when you're clinically sitting there and talking to her in the ER, that's not your first call, is that, right? She's got an aortic dissection. So put her in a CT scanner and then boom, there it is. So it's hard for me to imagine why you wouldn't jump in one. But so there's also, I'll give you a couple of links to some CT sites where you can go and see some of these clinical examples. They're absolutely amazing. Yeah. Oh, the color maps can be done. So the question was, how do you add color to the CT scan? Because it looks like we've got red and white going on here instead of just, grayscale brightness. And so color mapping is done usually in CT when you only have one energy involved, and it truly is just, grayscale brightness. You then just assign colors as a function of brightness, right? And you can make things that once they reach a critical brightness, you can turn them some color, right? And suppose you want to find something that it has to have a Hounsfield unit of 130 or more, right? So all you do is turn everything in the field of view that has 130 or more red, and then it makes them stand out. 130 didn't come out of space. That's what you do for calcium scanning, to look for calcium in your coronary arteries. So computer tomography, as these technologies increased in, I want to say, fidelity, and they became faster and the images just became better and better, usage pretty well exponentially increased, right? And I can't find any new data. I think the radiology community probably stopped making these graphs because it's like a target for increased healthcare expenses. It's like, well, look at that graph, and the CTs are going up like this, right? And so it's 2007. So here's 95, 2 million. So this is ER visits, right? This is probably covered by Medicare because that's where you have good data, is everybody who gets paid by Medicare. And so number of visits with CT, and just the relative numbers, it goes up by a factor of 8 over a very short period of time. And so it's going up to here, now probably. And it's basically more caution is used for younger patients, because to expose somebody to x-rays when they're younger, you have to have probably a higher necessity to see what you want to see, because they have their whole life ahead of them to develop a cancer based on whatever mutation occurred from those x-rays, right? So x-rays don't come for free, in the sense that it's ionizing radiation. You will break DNA bonds. They will get repaired 99.9% of the time. Sometimes they get repaired wrong, right? And then that sets off a cascade, which is not good. So, but what is known about that is at dose levels that are quite high, actually. Not a lot known with very low doses. So here's a 3D image of a coronary vasculature in a CT scan. So this image was taken in 140 milliseconds, and that shows you all of the vessels on the surface of the heart to try and diagnose coronary disease. Here's a set of, these slides will be up on the Canvas site, so you can just look at these and find others that have, every vendor has a fantastic website just showing their spectacular best pictures, right? And it's really fun to go in there and look at it. So MRI, same basic time frame. We got these guys, one's on the West Coast, one's on the East Coast, and they discover NMR itself, the physics phenomenon. And then about the same time CT was done, Paul Lauterbur used that signal to make an image of 2 test tubes in his NMR spectrometer. So when these guys discovered NMR, people started looking at NMR spectra of many things. And it turns out in organic chemistry, it's fantastic. You can look at all of these spectra. People have, looked at wine, ID this, done that. NMR is a very useful tool. He used gradients, magnetic field gradients, to find out where the signal was coming from, and made this very basic picture. And then in the late 70s and early 80s, some of the pioneers made NMR scanners that are NMR spectrometers that you could put a person in, right? NMR spectrometers were available widely, and they were a popular thing in chemistry departments. Every chemistry department had 10 of them or something. But you didn't usually put people in, right? Because they just weren't big enough. And so here's a magnet with a person laying in it, and here's a group at Nottingham. They made a whole body scanner, and a bunch of these folks went on to companies to design, the first generation of commercial scanners. I love their haircuts. It's like the Beatles, they're like Beatle cuts, right? And this is like in the 70s. But anyway, this is what a modern MR scanner looks like. It has a behemoth of a magnet. This magnet is usually 10,000, 20,000 or more times the Earth's field. Okay, so it's a very strong magnetic field. And you put the patient into that magnetic field, and then you do your radio frequency emission from your coils, turn those off, and listen for radio frequency coming back from the patient. And this only occurs when they're in a magnetic field. You can't actually do it in the Earth's field, but the signal's very, very small. Right? So over the first 25 years of MR, 40 years, the push was to get bigger and bigger magnetic fields because the amount of signal coming back was bigger. The separation of chemical species gets bigger, so you can look at particular things. My PhD advisor, who was one of the early folks in MR, looked at it in the 70s and went into pi-meson therapy because he did back the envelope calculation, and he said, if this thing's ever going to work, you're going to need a magnet the size of a pickup truck, and it's going to cost $1 million. So no one's going to do this. And now we have many who aren't the size of a pickup truck. They're the size of a moving van, and they cost tens of millions of dollars, and people are doing it all over the world. So here are some of the big ones. This is 3T magnet here in Dr. Liu's center, 7T magnet in Minnesota. Look at this guy. This is a Neurospin 11.7 in France. And here's one that's still in England. It's going to be shipped to the NIH. So the deal is to get bigger and bigger magnets so that you can get higher and higher resolution pictures. The pictures from MR are absolutely spectacular. You get this soft tissue contrast between different types of tissue that you can modulate with many different ways of taking the scan to really customize your contrast so that you see the tissue you want to see, or you get the maximum contrast between that tissue and what's in the background. And there are different modes of generating different contrast between tissues, right? So it's really multimodal imaging inside the one scanner. And you can see these fantastic high resolution pictures of the brain. Here's a high resolution picture of MR angiography in the brain without injecting any contrast. And you just look at all the vessels without injecting anything into this patient. It's remarkable. And because the brain stays still, you can gather data for a long time, make very high resolution pictures. This shows what are basically T1 based or intensity based images on the bottom row. On the top row, it's that same slice in that person's brain, but the brightness here corresponds to how much blood flow flowed into that slice over the course of some time. You can adjust that time. And so you can make a perfusion map, right? And in fact, you can make a perfusion map without injecting in contrasts into the person. You can just label their blood with NMR itself. So you get these wonderful perfusion maps in the brain. So if somebody comes in, you think they might have a stroke or the flow is down in their brain, you can see that directly on the picture.
A lot of these images look very similar to CT. What would be, is it just like a cost thing? Why you use MRs?
That's a great question. So these images, specifically in the brain, images look similar to CT images. CT, for the most part, has one picture that it gives you of the brain. And that's, you get to choose the energy of the X-ray, and then it gives you the picture. This is one of an infinite number of contrasts you can get from MR of this brain, right? So if we go back to this picture, you can see NMR can change from the cerebral spinal fluid looking like it's got no signal or a negative signal to cerebral spinal fluid looking like it's the brightest thing in the brain. And then the contrast, here between this gray matter here the gray matter is the brighter stuff, and these white matter tracks here can also be emphasized by changing NMR parameters. And so even though you say, well, those could be CT images, it could, but the potential certainly the perfusion there is not CT images, right? So,
That's not just post-processing, that's like
oh no, that's not post-processing. You actually design the acquisition of the data and you run the scanner such that it labels slices with specific RF radiation, and then you watch that stuff flow into a slice. So you do dynamics, right? And that's done a lot in MR. And here's some other dynamics. This is basically taking MR acquisitions over, say, 16 heartbeats while a patient holds their breath. You can see they're holding their breath. The chest is very still. So this is a very compliant patient. They're not breathing. When you say, you're going to hold your breath for 12 heartbeats, and this patient actually did it. And you can see the blood in the left ventricle is very bright. This is the left ventricular muscle in the heart, sort of ejecting blood on each beat. And this is the right ventricle up here. There's, other stuff over here. So for cardiac function, after a 16-second acquisition, you get one of these movies, and it's very, very clear what's going on. You can look at that heart in a different orientation. In MR, the patient is in a bore lying down on the table, but you have infinite flexibility in terms of how you orient the scan plane. So you can now take a scan plane through the center of the heart with the long axis, so the apex of the heart is here, the valves are up here. And then on the next acquisition, you could use this acquisition to plan your next plane, which would be perpendicular to this one, for example. So then you can see really nice estimates of motion, of wall thickening, of function here. So that's dynamic MR, and that's taken not in real time, actually. That's actually gated. So you usually take 16 heartbeats and you break up the time between each beat to say, the first 16th. And then over the 16 heartbeats, you fill in the data for that first 16th using each beat. And you assume that each beat is equivalent. If it's not, the image comes out looking pretty bad. So it's something going wrong. If it is, you get these beautiful pictures. You can compensate for some missing data. Here is a really cool application of MR, which they're world famous for this stuff here, where you isolate a certain part of the brain, you give the patient a task, say, a simple one is just tapping their finger, or another one could be thinking a specific, or having them respond to a specific chest position, something like that. And then when that response is turned off and on, you watch the signal in their brain go up and down in lockstep or in phase with that response. And so you do that over and over again, and you can see which parts of the brain light up when that task is being done versus the control. And so this is a huge field. It's called functional MRI, where you can essentially do a lot of cognitive function research in an MR scanner. This is measuring fiber tracts in the brain using what's called diffusion MR, where you measure which way the water in the brain can flow most easily, or let's say not flow, can move most easily. So it might be inside a cell, but there's a direction that it can move more easily than a perpendicular direction. And that turns out to map out fiber tracts of these neurons in the brain. And so you get these beautiful maps of how the neurons are interconnected. Okay, any questions? So that's a quick introduction to CT, quick introduction to MR. I think you sensed my bias in terms of whether or not these are valuable techniques or not to medicine. Any questions about that? No? Okay. If you have any questions, just put your hand up, because it becomes more informative, actually, if I know if you're understanding stuff. Okay, so we're going to look at image quality briefly. We finish at, what time do we finish? 12:20? Is that right? Yeah, okay, good, thanks. So here's 3 different imaging techniques. This on the part A is CT, where the contrast is very low between the different types of brain tissue. However, the contrast is very high between very fine bone structure and the brain tissue. So we're actually looking at a component of the CT image that's up at the bone level here. MR, and this is positron emission tomography, or PET, it's called. So you can see there are different looks about these. The contrast is different in this one. Obviously, the spatial resolution is different in this one. It looks blurry, right? Yeah. Okay, the question, that's an excellent question. Can you generally say that MRI is safer than CT? You can if you don't have an accident, right? So the problem with MR and the way people die in an MR scanner is very large metal objects hit them going at high velocity, right? So if you walk into an MR scanner and there's an oxygen bottle under a bed sheet, that oxygen bottle will not stay on that bed sheet when it rolls up to the scanner. And those of us who've been doing MR long enough have seen a number of these things happen, right? Luckily, I've never seen anybody seriously injured, but I have seen parts of MR scanners destroyed, right? By, in my case, it was an oxygen bottle that flew into the scanner. Somebody went in unsupervised, one of the staff flew into the scanner, the bottle hit the head coil, the regulator on the bottle snapped off, and that bottle evacuated all of its high pressure oxygen right there, made a crazy noise, and it didn't move an inch, right? Normally that thing would fly across the room, but it just stuck in that scanner. So the other thing is if you have, say, a pair of scissors or a wrench, say, and you walk into an MR scanner and you forgot you had the scissors in your pocket or the wrench in your hand, when you feel it pull, when you feel the magnetic field grab the thing and pull it, it's too late. You're not holding that thing, right? It's gone. And it's spectacular to watch it go, right? So that's the problem with MR. The main problem, that's how people have died at MR scanners, mostly. MR also has a side effect where you heat people because you use radio frequency radiation. And so if you're really big, then you will absorb a lot of RF and you'll get warm. Literally, you just get warm, right? And so that's a hazard. In CT, the primary hazard is the long-term effects of the small amount of radiation that you've been exposed to. And that is a field that's been studied extensively. And if somebody wants to do a project on that, that'd be great, because it's not a trivial problem. CT doses of X-ray that are used now commonly in CT have been reduced by about a factor of 10 in the last decade. And this is due to advanced reconstruction techniques. You just don't need the signal to noise on the raw data that you used to make the radiologist happy with the picture. You can infer what the underlying image is with high fidelity using techniques as opposed to using more photons, right, to do it. So what used to be a 20 millisievert exam is now commonly a 2 or 3 millisievert exam. And so that risk has been reduced considerably. That's a great question. They both have their issues. Both of them also improve many of their applications when you inject a contrast agent into the patient. And so you have a very rare event where the patient is allergic to the contrast and you didn't know that. And so they might have some kind of anaphylactic reaction to the contrast. Yeah, it's not pleasant when it happens. No. And very uncomfortable for the person who went through it. And it, is something that everybody fears actually is going to happen. And procedures are in place when it happens, but it's not a good day. Okay, so image quality. Here are some of the definitions of things we're going to look at. Contrast, i.e. your target could be a tumor, and the background could be, say it's tumor in a liver, tumor in a lung. You have a background and a target, and just you want the signal to be as different as possible between those two things to detect it. Spatial resolution. Can you differentiate two small things that are close together? Right? Can you detect a channel in something? You know, the other thing is, can you detect a small object at all? So if it's a tiny piece of calcium in a coronary artery, is it below the size of detection? Right? So that's all spatial resolution. Temporal resolution is, it comes in kind of two forms. One is, can you watch the physiology at the appropriate time scale? Do you get enough images to actually see an increase in signal such that you can measure blood flow, for example? And the other is what you would call the intra-scan temporal resolution. Was how long does your shutter, for lack of a better word, have to be open to collect the signal, right? So you can imagine if I have a camera and I'm taking a picture of some event like a football going across here, and I can take a picture at 1,000th of a second, like really quick, but I can only take it once a second. That's not going to do you much good because you're not seeing the trajectory, right? If we ratchet it back and say, well, instead of 1,000th of a second, I'll take some local blur. I'll do it, maybe I'll open my shutter so it's 100th of a second. So 10 times longer. So then, but now I can get more pictures. So I get a slightly blurrier picture, but I get 10 of them, right? And so now I can see the arc. So depending on your application, those two types of spatial resolution or temporal resolution get traded off. And that happens in MR and in CT. Noise is usually in MR, it's the noise actually is a natural phenomenon. If you take a coil and you don't elicit a signal from the patient, but you have your receiver coil that you're going to listen to the signal. I just hold it away from the patient and look at this, basically scope and watch the random noise and that's coming from the thermal radiation or the thermal effects on the coil. When I put it up against the patient, the noise goes, it gets bigger. So the noise, the patient is a source of noise. The Brownian motion of all the things in the patient, right? And that noise is very well behaved. It's Gaussian, it's white. It means it has, all frequencies are in there. In CT, the noise is essentially lack of detection of photons. So if I have my photon detector and I put a very bright X-ray flashlight and every element on my detector gets at least 300 counts, then I'm very confident in the number of counts that hit every detector, right? Now I turn down my X-rays so that I do low dose imaging. And in some of my detectors, I'm getting 2, 3, 8 X-rays. So now I'm not that confident about how many are actually there because the noise, the counting statistics gets worse, right? So that's a source of noise on CT. And then there's underlying electronic noise in all of this. Yeah.
I guess that's the sort of the trade-off is you want low intensity X-rays to minimize the chance of radiation damage, but,
Right.
But you get a higher noise because you have less detection.
Exactly. And we'll take a look at some pictures where we just like cut the amount of X-rays by a factor of 4, and let's see what happens to the picture. Right. And then signal to noise ratio is how much signal do I have divided by how much noise I have. If I don't have any signal in there, just measure the noise. And now I have signal. What's that ratio? Very simple. In contrast to noise, if I have two objects, one's a target, one's a background. What is the signal difference between those two objects divided by the noise? We're going to look a lot at a linear systems approach of how this goes. And this is because that's how Princeton Links do it in their book. And so we'll look at signals and characterizing signals with their Fourier components, or how does a modulation in my picture get transferred through my imaging system. So this is a picture of vertical stripes, right? And the vertical stripes have a certain brightness in this picture, and it's less bright here, less bright here, less bright here. And these vertical stripes occur at a very specific frequency. The question of our imaging system is, do those vertical stripes go through our imaging system and remain with this contrast? Or as the vertical stripes get higher frequency, or at this frequency, does our imaging system attenuate that frequency? That's the basis of all of this. And that is, I have an input of a sine wave, goes into my imaging system. What comes out? Does it get attenuated? Does that frequency get attenuated? And we ask that question for all possible input frequencies, right? So the minimum input frequency is if this sine wave is a constant, it's just a DC value, how bright is the whole field and there's no change on the field, versus a sine wave of a specific frequency. And then we'll look at a sine wave of a higher frequency, higher frequency, higher frequency. Eventually, the stripes are so close together, the imaging system cannot detect that there are stripes there, right? They're just too close together. That happens in every imaging system, right? And the question is, at what frequency does that happen? At what frequency of stripes does that cutoff occur that I just say, I can't see those anymore? So here is a CT image of a phantom that we had made here in the machine shop. Really good machine shop here, by the way, because they made some very small holes in this phantom. And so their holes are drilled in plastic. And so in CT, you get a signal of -1,000. We'll figure this out later, where there's air. And here, I think the signal is about 100. Okay, so there's a high contrast between what's in the hole, which is air, and the background. And then compare it with that picture. So I'm going to flip back and forth. Okay, so 230, 300 MA, 380, say 400 MA, 100 MA, 400, 100. So that's basically 4 times more radiation than that. So if our job requires us to detect how many holes are right here, this won't do the trick, right? We can't see it, right? This one, we can see probably that. Right? And so the reason that this quality gets better is just you have higher counts on your detector. And when you go to reconstruct it, you don't have to smooth out the data, right, in the raw data in order to make that reconstruction. And so we can quantify, basically, if I draw a profile through this, and in some of your problem sets, you'll do this with image J, which is a very simple imaging analysis thing. And you look at the modulation of the signal, and these are the units, the gray value or Hounsfield units for CT, between 100 and 150 here. And then that's what it looks like when you cut the radiation by 4. So basically you don't see that signal. So that frequency is now beyond our perception, right? Another way of looking at resolution, I'll just do one thing, is if I image a tiny little dot, say I have, what we use in the CT scanner is we take really good Japanese pens and we take the ballpoint out of them with a pair of pliers. Let's take it out, and it's like 0.25 millimeter little piece of tungsten or something. And you put that in the scanner and image it. It doesn't come out as a 0.25 millimeter object. It comes out as a Gaussian, which is like a blurred version of that object. And so here's our ballpoint pen, and then this is what the scanner returns, right? And so that's the smallest thing the scanner can image, right? It looks like this. It's called the point spread function. And then when we have 2 of those objects, we can bring them closer together and ask the question, when can you not determine there's 2 things there, right? Because this point spread function overlaps. And so that's another definition of spatial resolution. It's just when these get together and you add it up, it just looks like one blob now, right? Whereas here it looked like two blobs. And so that's a sort of a Raleigh definition of spatial resolution.